Out of control.
All right, let's get started. Get the lights and whatnot adjusted. Okay, so just a quick recap on logistics and whatnot. Y'all had your celebration. I am still in the process of grading that. My goal is to get that back to you on Monday, but I also have the massive pile of steel exams I still have to get through. I know I keep saying I'm going to get those done, but I have a lot of people in there. So my goal is to get both of those back to you on Monday. We'll see. Homework 6, you all just got that back. Homework 7, you'll just turn that in, so that's still being graded. As for what's remaining, we only have 2 homework assignments remaining. The one on development length, which we're starting development length today. I'd argue that of all the topics that we do in concrete design, development length seems the nastiest. I mean, this is the equation for development length, and it looks horrible. But honestly, it's probably one of the easiest things that we do. It's also one of the easiest things, I think, to understand. There are a lot of parameters going into development length, but by and large, it's a pretty straightforward thing to compute. And then our last big topic is on columns and beam columns. Okay, so with that, I'm just going to go ahead and get right into it. So before I jump into development length, or to try and sort of introduce the idea or introduce the concept, I want to talk about, it would help if I turn that on. I want to talk about a pretty basic design scenario. Now, we've sort of beaten problems like this into the ground until we're blue in the face. But let's just sort of get back to basics. Okay, so we have a beam, simply supported. We'll say it's 30 foot long, doesn't really matter. And I have a load on it. And I have here the loads factored. We'll say it's like 5.5 kips per foot. So if we were in beam design mode and we were trying to design, let's say, the size of the beam, or trying to determine the amount of reinforcement or what have you, one of the first things that we would do is we'd say, okay, let's try and compute MU. All right? And if you have a simply supported beam and a uniformly distributed load, what's your MU going to be? By now, that should be old hat. W squared over 8, exactly. So now here's the thing. We've been using that for our formula for moment because it does reflect the maximum bending moment, right? Go back to basic statics or structural analysis, and you have a simply supported beam with a uniformly distributed load. And so you're right, WL squared over 8 tells you that that's the bending moment at midspan. And so that's the point I really want to make. That's the moment right here, okay? Okay, so think about that. What we've been doing up until now is we've been saying, all right, let's take a beam, let's compute its maximum moment, and let's determine the reinforcement required to resist that moment, okay? And then we say, all right, here's our beam. We, calculate an MU, and then we say, okay, what's MN, what's our reinforcement ratio, and so on and so forth, until we determine the area of steel, right? Well, here's my question. Do we really need to use that steel everywhere? Think about it. Here's a beam. The beam that we're looking at for this problem is just a rectangular beam, and we have 1, 2, 3, 4, 5, 6 bars. Do we really need to use 6 bars of reinforcement everywhere? Because this moment value is only the moment right here in the middle. I mean, I'd argue we need 6 bars of reinforcement right here, but do we really need it like right there or right there where the moments are very, very small? Well, I think theoretically you could argue no, you don't. And so how would a theoretician handle it? Well, they'd say, all right, let's dig a little further into the statics and the structural analysis. Remember our secret weapon of structural engineering, the samurai sword or the lightsaber if you're a sci-fi fan. We'll cut a section through the beam at some distance x, right? This is stuff y'all did back in 312. And say, okay, I'm cutting it at x. I've got WL over 2 times some moment arm rotating this way. I have an internal moment that I don't know going this way, and WX times x over 2 that way, and I can determine an equation for what that moment diagram looks like, right? And so I can say, all right, that equation makes sense, right? It's in the domain of x squared. It's a parabola. It's negative x squared because it's going downward. And that looks exactly like what our moment diagram should look like. And so I can take this beam and I can say, well, I know enough now to know what is, like, this is how I'm going to determine the capacity of that beam, right? ASFY times D minus A over 2. And then I adjust it by a phi value. And I could say, well, let's try and keep this symmetric. I can figure out what the capacity is if I had, say, 6 bars. But what if I wanted to try and trim that reinforcement a bit? What if I only wanted to use 4 bars? Or what if I only wanted to use, let's say, 2 bars? Well, what I could do is I could say, let's try and figure out what the flexural capacity is for each of those cases, and it's just plug and chug. And then next thing I could do is say, well, where do those points occur on the moment diagram? So here's my moment diagram. And so what I'm saying is, I know what the maximum capacity is, and so here I'm saying I need 6 bars of reinforcement. But where, let's say, where on the moment diagram could I start using, let's say, 4 bars? And maybe where on the bending moment diagram could I start using 2 bars? And so instead of trying to use 6 bars along the entire beam, maybe I could do something like this. Maybe I could trim it up a bit, make the beam a little more lean, Only use, the reinforcement where I need it. Only use the 6 bars of reinforcement where the moments are really, really high, okay? Whereas where the moments are really, really low near the support, I only use, say, 2. Does that concept kind of make sense? All right, now let me ask you a question. How many of you think we actually do this in the field? Raise your hand if you think we actually do this. That's good, because we don't, all right? We end up just using the reinforcement across the board, okay? Now, that might sacrifice some economy, but now we need to drop a truth bomb on the whole thing, okay? Everything up until now has just been theoretical, okay? And there's a very significant point about reinforced concrete design that we're not talking about, okay? Now, in order to explain this new concept, I'm going to need a volunteer. One of y'all, it'd be easier. Pick somebody volunteer. Okay. All right. Here's what we're going to do. He and I are going to engage in a game of tug of war. Now, here's the rule. All right. You can only hold the blue part of the rope. I hold the white part of the rope. That's the deal.
All right.
You up for it?
Yeah.
Okay. You heard this, right? Okay. There you go. Please don't hurt yourself. All right. 1, 2, 3. Oh, good job. What happened? I mean, I know I'm a pretty physically intimidating guy. I know, but in all honesty, you didn't win. But here's the thing: even if he was Bruce Banner or Thor or somebody, was he ever going to win? The answer is no, because he didn't have a good enough grip on this string, right? Okay. This example is theoretical, but it's not taking into account a very significant concept. Okay, how many of you all have ever seen what rebar looks like? It looks like this, right? Okay, it's not smooth bars. If you take a look at rebar, it's got these little ribs on it. What are those ribs for? Okay, they're for bonding with the adjacent concrete, right? Okay, so let me give you the sort of the concrete design analogy to what we just did. Okay, imagine that this was a big wall of concrete, and I had a piece of rebar embedded inside the wall. If the rebar was only embedded this far, I could probably easily yank it out, right? Whereas if the bar was embedded, say, 1,000 miles into the wall, that's not happening, right? I'd have to be from Krypton to make that work, okay? The reason why is because the farther that embedment occurs, the stronger the grip. And the reason why is because of these ribs. The farther the rebar is embedded into the adjacent concrete element, the more contact that concrete is going to have with those ribs of that reinforcing bar, and ultimately, I'm going to develop a stronger grip. Now, here's the thing. Let's go back to that analogy of the bar in the wall, okay? So if the bar is only embedded this far into the wall, like a very short amount, and I start yanking on it, one of two things is going to happen. I'm either going to fail the rebar or I'm going to fail the concrete. And I would argue that if the bar is only embedded this far into the concrete, that I'm just going to crack the concrete right there around the bar. Does that make sense? Okay. Now, the flip side is, what if that bar is embedded 1,000 miles? Well, I would argue that the concrete is going to have a pretty strong grip on that bar. And I'm going to yank on it and yank on it and yank on it. And what's going to happen is I'm not going to fail the concrete. Instead, I'm going to fail the bar. Okay? And so what we're trying to do, what we're trying to figure out is this. When we design a reinforced concrete beam, what do we do for our assumptions when it comes to stresses? Well, the concrete, we assume it's 0.85 FC prime in compression, right? But what do we assume for the steel that's in tension? What stress do we assume for the steel? You about to say something. What was it? Fy, right? So ultimately what we're trying to do is figure out how far that bar needs to be embedded in the adjacent element such that it hits Fy. In other words, such that it hits, or such that it develops its full capacities. That's what I mean by this concept of development length. Now, I want to show you something real quick. What happens, let's go back to the analogy of the wall and the concrete. What happens with bond failure, so imagine I have that bar embedded into that wall. What happens if I actually start yanking on it? So let's say I have a bar right here. So this is a bar of steel or a rebar, and it's sticking out of the wall and I'm yanking on it. Okay, and let's say, here's the beam in consideration, and it goes on like this. Well, if you start yanking on it and you start looking at the failure of the concrete, what happens is it starts to fail in kind of like a cylindrical fashion. Like you'll start to get cracks that sort of jut out, sort of like this, almost in a cylindrical fashion. And so that cracked, that failure region will sort of expand like this. It'll expand it'll go like that. And what will happen is those cracks will continue to propagate until you hit one of three distances. You either hit right here, you either hit right here, or if you have another bar over here, you hit halfway over. Because the idea is you're yanking on them all, so this one's going to be cracking as well. And so I just want you to keep these three distances in mind because they're going to pop up here in a second. Now, if the concept of development length is a little strange, let me go back to the analogy of the tug of war. Okay, so here's the thing. He was holding the rope that was about this long. Okay, now how much rope did I have? What was it, about 6 feet or so, something like that? Would it have really mattered if I had 600 feet? Would it really have made a difference? Probably not. In other words, there is some value that caps it off, right? Going back to the analogy of the wall, if I have a bar stick, in a mass of concrete and it's embedded 1,000 miles, well, that's a really, really long development length. It probably doesn't need to be 1,000 miles long, just like I didn't need 600 feet. I really only needed about 6 feet of rope, and I was going to win that tug of war every time. So what is that magical value? Okay, and this right here, this example, I think, this conceptual example, I think hammers it home more than any other. So I have here a cantilevered beam. Okay, so I'm gonna erase this because I wanna make this point. This is really important. So I have here a cantilevered beam. Okay, and it's framed into a column or to an element over here. Okay, now this is a cantilevered beam. So in a cantilevered beam, where's the reinforcement go? On the top or the bottom? The top, right? Did you say bottom? No, it goes on top. Remember, concrete on top is in tension because it's being bent this way, right? So remember, if you have a cantilevered beam, you put the reinforcement on top. See, if this is, like a party deck, and people are dancing, and you have a disco ball right here, and you put the reinforcement on the bottom, that's going to be a short party because then the concrete that's in tension has no reinforcement, and it's going to crack like crazy, right? Now, here's another thing, though. Let's go back to basic structural analysis. Where is the largest bending moment on this section? It's right here, right? It's at the support, right? So when you design the section, you're designing for the moment right here. But if all you do is say, well, oh, great, I'll just take the reinforcement, place it right there, and I'm good. No, you're not good. This concrete has to be able to develop its full capacity. When you're bending on this, you're yanking on this bar. In order for this bar to work, it has to be embedded a certain length into that adjacent element. How far does it need to be developed, or how far does it need to be embedded? I propose that that length is the development length, L sub D. Okay? In other words, you can think of L sub D as that 6 feet of rope. Really wouldn't have mattered if I had 600 feet of rope. I really only needed 6 feet of rope to win that tug of war every time, just like this piece of rebar is only going to need L sub D in order to be able to develop its full capacity. Does that idea make sense? Okay. All right. Any questions about the concepts? All right. Let's get into the math. Now, this equation looks nasty, but I promise you this is probably one of the easiest equations that we deal with this semester, or the easiest processes we deal with. First off, while there's a lot going on, there's also a lot of things that are very, very familiar. For instance, everybody in here has seen a square root of FC prime, right? Remember, you put in PSI, you get out PSI. We've already seen lambda show up a few times. That's our lightweight aggregate factor, so that's no different. F sub y, that's no different. And then D sub B, that's just the diameter of the bar that you're looking at. If you're looking at a number 6 rebar, what's the diameter of a number 6? Anybody remember how you do that? 6/8, right? Anything up to a number 8, the diameter is just that number divided by 8. So that's really easy. The only thing that's new are some of these factors in the denominator and these psi factors. And each of these psi factors, I think when you start exploring them one by one, they're really easy to understand why they're there. Okay, so I'm going to take each one of them one at a time. We have a psi sub t, a psi sub e, and a psi sub s. Let's take the first one, the psi sub t. Psi sub t is our reinforcement location factor. The reason why it's called psi sub t is because it sort of stands for top bars. Okay, now, here's the thing. I'm not talking about situations like this where it matters whether or not the bars are in tension or compression. I don't care if it's a singly reinforced beam or a doubly reinforced beam. I don't care about any of that in regards to development length. There's a very significant reason why we need to account for top bars, and it's a really simple reason. It's basically just gravity. Okay? How many of you have had 321, have had materials lab? Or how many of you have ever cast a concrete cylinder or done any concrete work in the backyard? Okay, so you're casting a cylinder, right? Tell me how you fill the cylinder up. What do you do? Somebody tell me. Me. You tamp it, right? And then you fill some more. And there we go. Why do you do that? Air voids. That's it. So here's the reason why you have a top bar factor. If you have, let's say a concrete beam that's, such and such deep, we're talking about bond strength here. We're talking about how well the concrete comes into contact with the steel. I would argue that if I'm just filling this form up with concrete, that just because of gravity, I'm going to have more air voids up here than I am down here. That's just gravity, right? So I would propose that bars on the bottom have a better bond strength than bars on the top. So the way that we handle that from a development length perspective is we say that if we're dealing with bars on the top, we multiply our development length by 1.3. We say if you're dealing with bars on the top, you need 30% more development length than you are bars on the bottom. Why? Gravity. Okay, and how do you define top bars? A top bar is defined for any bar where this dimension here is greater than or equal to 12 inches. So that just comes from doing laboratory tests and determining where's the dividing line for simply computing development length. So does that make sense? All right, everybody good there? Okay, now what about psi sub e? What about our next one? Psi sub e is called our bar coating factor, but the reason it's called psi sub e is because it stands for epoxy. How many of you all have ever seen rebar that looks like this? That green looking rebar. So why do we do that? Like, why do we have this green? Is it painted green? No, it's like a plastic epoxy, like rubber coating. And why do we do that? Corrosion, yeah. So definitely if you're looking at rebar that's being placed in an exterior setting, like a deck on a highway bridge or something like that, you're going to see epoxy-coated rebar. Now, why do we care? What does that have to do with this? What does that have to do with development length or bond strength? It's there you go. That's a great way of putting it. Slip doesn't stick. It's slippery. Epoxy-coated rebar is slippery, okay? And as a result, if you're dealing with epoxy-coated rebar, you have to embed that into the adjacent element further, okay? That make sense? So here's how we handle that. We get a little more refined with epoxy-coated bars. So first off, if we don't have epoxy-coated bars at all, we don't have to worry about it. We just take psi E to be 1. If we are dealing with epoxy-coated bars, it depends on our cover and our spacing. So what I would say, this is the easiest way I would describe it verbally, if we have epoxy-coated bars, but they're spaced really close together, or they have a really small cover, then we really got to bump up our development length. We've got to bump it up 50%. If we're using epoxy-coated bars, but we have ample cover and ample spacing, then we only need to bump it up 20%. And how am I defining, wide spacing and ample cover? How am I doing that? Well, epoxy-coated bars with a cover less than 3 times the bar diameter. Remember, what's the cover? It's from the center of the bar to the edge, right? So if that cover is less than 3 bar diameters, or the spacing between bars is less than 6 bar diameters, which happens more times than you would think, we got to bump that development length up 50%. That's a pretty long development length, but it depends on the scenario. I mean, if we're casting a bridge deck in West Virginia where you've got road salts on the road and all sorts of stuff going on, well, you might have to use this stuff. So just something to keep in mind. Does that make sense? Okay. All right. Let's talk about psi sub s. Psi sub s is our reinforcement size factor. This one takes a little bit of thought, but it's not that bad when you chug it out. So let's go back to beam design. So what's our general process when we design a beam? We'll have some moments, and we take those moments and we say, okay, let's compute a nominal capacity that's required. Then we figure out what our reinforcement ratio is. Then we figure out what this is, right? Y'all remember that? Now, we have a required area of steel, but how do you figure out what you use, right? You have an area of steel that's required that's 4.5 square inches. How do you figure out whether you're using 3 number 9s or 4 number 7s or whatnot? How do you figure that out? You got the spacing in that bar chart, right? So let me ask you a question. For a given reinforcement requirement, you could probably use a few really big bars or a whole lot of really tiny bars. Like you could use like 20 number 3s or 1 number 14. You could do either one, right? And theoretically, they could have about the same area, all right? Now, up until now, I've been saying that if you had the same area, what should you do? Say it again? Use the one that has less bars, because that's less handling for the contractor and for the construction workers and whatnot. That fewer bars means less handling. But there actually is a benefit to using more tiny bars. And the reason I'm mentioning this is because we're going to start computing development lengths here in a little bit, and they're going to be kind of long. And so the question is, well, what happens if you don't have room? Like if you need 50 inches of development length and you only have 30, then what do? Well, you got to start coming up with solutions, and one solution is to use a bunch of tiny bars. Now, what's the logic behind it? If you have one really big bar versus a bunch of really tiny bars, they might have the same cross-sectional area, but by using more bars, you have more surface area of those bars. And more surface area of those individual bars means more surface for the concrete to grip to. More surface for the concrete to grip to means you don't need as much development length. And so the way that we handle that from a spec perspective is we say if you're using any reinforcement that's a number 6 bar or smaller, we can reduce our development length by 20%. We can use a psi factor of 0.8. But if you're using a number 7, number 8, any other larger bar, just take a psi to be 1. Does that make sense? Okay. Any questions so far? All right. Okay. Effect of spacing and cover. So this was that denominator in that equation. Now, we're going to do a few examples, and we're going to take them step by step in terms of complexity. So our first example, we're going to take this KTR value to be 0, so I'm going to lightly define that. But this C sub B value, what is this? It's that right there. Remember I told you that the way that concrete is going to crack, it's going to hit one of three distances, either here, here, or here. Well, C sub B is taken as the smallest of either what this distance is, that distance, or halfway between the next one. So we're going to do an example of that, and I think you'll find it's a pretty straightforward calc. This KTR value, I'm going to lightly define it now. I don't want to dump too many details on you all at once. But the long story short is KTR is a transverse reinforcement index. If you want to think of something we've been dealing with before, KTR is sort of a measure of how well your stirrups are doing. So you think you have bars going this way, but your stirrups wrap around them, right? Well, think, more stirrups mean they're going to confine that concrete a little better, and they're going to provide a benefit from a development length perspective because you're going to hold everything in so that concrete's going to grip a little better. So I'm going to just sort of move past this now. I don't want to get too heavy into the details, and don't worry, we're going to investigate this pretty significantly. But basically, KTR is a measure of how effective your transverse reinforcement is performing. A couple final notes, and then we're gonna get into an example. But this limit here is just something you're going to want to check when you're doing your math. Whatever value you get for psi t and psi e, that product has to be less than or equal to 1.7. That just comes from the laboratory test looking at those types of specimens. You find that, you know, individually those factors work well, but sometimes if you're using a really high psi t value and a really high psi e value, you can get some development lengths that are a little wonky. So this is the spec's way of saying, let's hold that back a little bit. Let's limit that to 1.7. This limit right here, this one on the bottom, if you go back to beam design, remember how we would calculate like an area of steel required something like 4.5 inches squared, but we always picked a pattern that was a little bit bigger. So we always had a little bit more reinforcement than we needed. Well, you can reduce your development length based on that ratio of how much you needed versus how much you actually specified. And so that's another way of creatively decreasing your development length, is you can just put more reinforcement into the beam, and more reinforcement means you don't need to develop it as much. Now, the downside is you can't do that too much, because then you start getting into, you know, a compression controlled section, and that's no good. Sound good? Let's stop talking. Let's start doing some number crunching. Okay, so what I have here is a beam that's a pretty straightforward standard beam, and we've got a few examples on development length that we're going to do, and as we go through this, you're going to see that the complexity, quote unquote, the complexity starts to ramp up a bit with each problem. But in the end, it's really not complicated. This is a pretty straightforward process. Okay, so I have a beam that's it's a regular singly reinforced beam. I got 3 number 8s. Here's the dimensions. Let me copy this here. Woo, that's big. All right. Okay. Now, remind me, I think this beam had an FC prime of, was it 4 or 3? 3 KSI. And what else can you tell me about the concrete? Normal weight. So it's normal weight, which means what? Lambda is 1. And Fy is 60. Good. Thank you. Now, let me go ahead and just write out our development length expression, just so everybody has it. And then we're going to break down each of these quantities one at a time. So L sub D is 3 over 40 FC, or sorry, yep, got that backwards. Fy over lambda square root of FC prime. And then we have our fraction here, psi T, psi E, psi S, and then D sub B. Okay. Now let's see if we can handle a couple things right off the bat. First off, What is d sub b? Well, d sub b is our bar diameter. We're trying to compute the development length of these bars here. So what's the diameter of a number 8 bar? Say it again? 1 inch, yeah. D sub b is, I'm going to say 8 over 8, which is 1 inch, because remember, anything up to a number 8, you divide the number by 8, and that tells you the bar diameter in inches. Okay. Now, we're going to do this example, I guess, twice. The first time we do it, we're going to assume that KTR equals 0, and then the next time we're going to compute KTR. And basically all I'm doing with that is I'm asking how does accounting for the stirrups help with the development length. So we'll get into that later. First off, though, let's check out each of these factors. Okay, let's take psi sub t. What is the value of, yes?
Do you have a stirrup in place without friction steel for the wraparound top?
You can. This image probably isn't the best. You can just have a single hoop. So, but yeah. I probably could have drawn like a couple number 3s there. The reason I left it off is because I didn't want you to think that we were computing development length of these. I just wanted you to focus on these. That's a fair point. But yeah, we could have like a couple number 3s there just to tie the cage together. Good question. Sound good? All right. So let's take each of these factors one at a time. So psi sub t, that's our bar location factor. What is psi sub t going to be for these bars? Well, let me ask you this. Are we dealing with top bars or are we dealing with bottom bars? Bottom bars. Okay. So say it again. 1. And that's a really good point that I want to make, is that typically these factors are all 1 when you're dealing with what I would call a standard case. Like top bars, they're not going to bond well, so you got to bump it up. And things like that. Like epoxy bars aren't going to bond well, so you got to bump it up. So this is going to be 1, and I'm going to say it's because we're dealing with bottom bars. What about psi sub e? What's the deal with psi sub e? What's that? It's uncoded, so it's 1. Exactly right. And so what I'm doing here in the calcs is I'm saying, okay, here's the value, and then next to it I'm saying y. Uncoded bars. All right? What about psi sub s? Say it again. 1. And why is that? There we go. 1.0, and we'll say bigger than number 6. So bigger bars, we don't have to worry about that decrease in development length. Now, off to the side, this seems like a little bit more than a formality at this point. I do want to do this because I'm going to try and do this for every problem. What is psi sub t times psi sub e equal to? That's just silly, pretty easy. It's 1, right? The big thing is that whatever we plug into that equation, that product has to be less than or equal to 1.7. Okay? If it's larger than 1.7, what that means is instead of plugging in an individual value here and an individual value here, we just plug in 1.7 for that entire product. And we are going to have an example show up later where we're going to do that. So just keep that in mind. Okay. Now, for now, we're going to take KTR to be 0. We're going to compute that later. So KTR equals 0. And I'm going to say for now. Okay. Oh, one other thing. KTR, the units are actually in inches. Like it's a length measurement. The final value that we need to determine is C sub B. So C sub B comes from this measurement here. So what we're going to do is we're going to take any one of these bars. Typically, you're going to look at the one on the corner, and you're going to say, okay, we're going to look at this bar, and we're going to ask ourselves, what are these three clear distances? So what is this distance right there? That's 3 inches because the whole beam's 18 inches high, and that's 15, so that's 3. what is this dimension right here? 2.5. And what is the dimension halfway over to the next adjacent bar? 1.5. So therefore, C sub B is always the smallest. It's 1.5. Because that thing, if I'm yanking on this concrete, it's going to fail, under that shortest distance. I'm not going to have to crack, or the cracks aren't going to have to travel as far. So that value is going to be less, or that value is going to be the smallest, the 1.5. Okay. Now, one other note that we need to check. C sub B plus KTR over D sub B. What is that? So this is 1.5 inches plus 0 inches over 1 inch. So that comes out to be what? 1.5. That quantity has to be less than or equal to 2.5. So it's sort of the same thing. If it ever is larger, we just use 2.5 in the expression. So that's good as well. Okay. So with all of this, we can compute the development length. So therefore, the development length is as follows. And the way that I like to do it is I just do it on one big fraction. So what do we have on let's do the bottom first. So on the bottom, what do we have? We have 40. And then so I'm just using this red equation up here. So we have 40 times lambda, which is 1, times the square root of 3,000. There we go. Make sure everybody paying attention. And then this fraction, but I don't need to plug that in like I did this fraction here. It's just 1.5. So we have 40 times 1 times the square root of 3,000 psi times 1.5. And then on the top, I have 3 times Fy. And what's my Fy? 60,000. There you go, right? Remember, the FC prime is in PSI, so this needs to be in PSI as well. So this is 60,000 PSI. And then our factors, so it's 1, 1, 1, and then our D sub B is 1 inch. So if you look at the units, what's the answer going to come out in terms of the units? It's going to be in inches. So our development length is going to be in inches. And so what does that come out to be? $54.7. Do I have a second? Yep. Okay, so 54.77, we'll say 54.8 inches. And typically, when you're looking at development length, remember, you're telling a contractor how far you need to embed the thing. Just tell them LD is 55 inches. So what that means is that for this scenario, we would need to embed that bar 55 inches into the adjacent element in order to develop its capacity. Now that's a long distance, right? So are there ways that we can correct that? Or are there ways that we can help that? Because that's a pretty far distance. I mean, I don't know that I've seen very many columns in buildings that are 55 inches in diameter. That's huge, okay? So one of the ways that we can handle that is fix that. Maybe we can encounter, or maybe we can use this KTR value. Let's see what happens with KTR. Let's say KTR is, what's that? Yeah. I'm sorry. So, yeah. So, well, actually, no. What we're going to do is this. We're going to try it with KTR is 0, and then KTR is computed. And then the next problem, we've got a couple different situations, because the next problem, we have 4 uncoded bars, and the parameters are a little different. So okay. No, we're still on 16A. Okay. So let's see what KTR does to our development length. Does it make things a little better?
Is that the length of the bar
No. So that's a good question. Are you talking about KTR or LD?
LD.
LD. So that's a good question. LD, the nice thing about the LD computation is it's actually completely independent of the loads. See, all we're asking is how far does that, what does that length need to be so that when I do an analysis, I assume that the bar can hit Fy. Okay? So as long as I can assume that the bar can hit Fy, I can assume that for any load scenario. Like if I have a beam, that beam could have a simply supported load on it, it could have point loads on it, it could have whatever on it, and when I compute the capacity, I'm saying that, Mn is ASFy d minus A over 2. Well, by doing that, I'm assuming the bar hits Fy, so that development length needs to be this. Now, it doesn't change the fact that that is a really long development length. So can we make it a little better? Yeah, we can, and there's a number of things that we're going to do over the next few examples to sort of fix that problem. Yes?
Does that mean for every problem that we've done so far, we assume the development length is good?
Yes. Yes, that's a great question, and the answer is yes.
This is kind of a different question, but development length only takes place for cantilever beams, right?
No. It's just for any bar in any situation.
Okay.
So this beam would not be cantilever. This would be a simply supported beam.
So what are, okay. So what would the rebar go into, I guess, on a simply supported beam?
I'll show you that here in a second.
Okay, maybe this is another dumb question, but it seems like the LD equation only takes into consideration the diameter of one bar.
Mm-hmm.
3 bars.
Mm-hmm.
And you talked about the overall area of steel.
Yes. Well, we've typically been using the same bar size. Like it's 3 number 8s.
I mean, to me, it just seems like DB should be like 3 times the bar diameter. What am I not doing?
Well, no, what I'm saying is each bar needs to be embedded 55 inches, not one bar. Do you see what I mean?
So it's just considering each bar.
Yes. But each bar is the same.
It just seems like if we had more bars, it'd be like this much.
So if we had
But here's another thing. If you think about this from a design perspective, if you used more bars, you would probably be using smaller bars. And that would be handled with your size factor. Your size factor would reduce the development length, remember? Does that make sense? Yes. Man, y'all are good. This is good stuff.
What if you just need, like, say, number 4 bars?
Yes. Like in a slab? Or?
Yeah, sure. I mean, just in a scenario where say you need 3 number 4 bars.
Yes.
Instead of, would
Th-
you still
Then
apply-
you'd apply the same equation, you'd just be able to use 0.8 here. But there's a lot of other things there's a lot of other corrections that we can make that we're not talking about. And it's one of those we got to walk before we can run, scenarios. You had a question, didn't you?
Yeah.
No, you go ahead.
I was just saying, I don't really understand why you would apply the size factor if you're not reducing the size. Like, you see what I'm saying? Like you have.
No, I don't.
So like if the design was just already 3 number 4 bars instead of number 8, you're not adding number of bars.
Yes.
So why would you still apply this?
Well, I'd argue for typical beams, like you're talking about a beam that would have 3 number 4s. And I'm saying that beams typically don't have 3 number 4s. Like that is a really small amount of reinforcement that you just don't see in a beam. I mean, if you have a beam that's 20 foot long that only has 3 number 4s in it, I'd like to see how big that beam is. Because that beam is probably tiny and isn't seeing any load and might crack under its own self-weight. I mean, that's a very light amount of reinforcement. And so I just don't think practically that it would happen, okay? Now, you had asked a question about the, like, how does this get, like where does this get used in a simply supported beam? I want to go back to, because this is good stuff, and we got plenty of time, so I basically want to go back to this problem here, and this is sort of where I was wanting to close it, is the reason we don't do this is because theoretically we could stop the bar here, right? But ultimately what I'm saying is you could stop the bar here plus its development length. Here plus its development length. And if you're going to do that, you might as well just extend them along the entire length. Does that make sense? And does that make sense to everybody else? Now, here's another thing, okay? There's a lot of issues that we're not talking about and a lot of ways that we can reduce the development length. I want to show you something. We're not going to play the tug of war, but just hold that real quick. I made a very conscious decision during the tug of war to do this. I want everybody to see this, to do this. Now, what would have happened if I did this? Does that make it easier for me? Oh, yeah. You see what I mean? I'm barely even tugging on it, and you're, I can see it. Calisthenics. One of the ways that we can improve development length is we can bend the bars. In other words, how would the development length of a bar change if the bar was bent into a hook? Okay? So what I'm getting at is what we just did now was probably the absolute worst case scenario for development length, and there's a lot of different ways that we can improve that development length. To give you an idea of the numbers, the development length that we just computed is 55 inches, and when we're all said and done, we're going to be computing development lengths that are 18 inches. You see what I mean? That's going to take that and really suck it in. But in order to do that, we got a lot of little things we have to get through. Does that make sense? Let me see if I can get through the KTR one, and then we'll call it for today. So let me show you the KTR value. Yes?
Looking at that kind of L-shaped rebar.
Yes.
So whenever we were addressing the cracking about the rebar earlier, it was in a circular fashion. Would that be?
Oh, the mechanics change.
Yeah.
Oh, yeah, you're exactly right. And the expression that we use and the way that we compute it gets way different for hooks. So you're exactly right. Yeah, it's different. We will get there, I promise. I promise. All right, let me see if I can do this KTR computation real quick. So KTR is computed as follows. So you compute KTR by taking 40 times the area of the transverse reinforcement over S times N, okay? And so let me explain where these values are coming from, because it's really, really easy, okay? All right. First off, N is really easy. N is the number of bars in a layer that we're considering. So how many number 8s are we considering? 3. So N is 3. That's easy. So 40, 3. The other two parameters are also just as easy. This ATR and this S are related to your transverse reinforcement. And if we're talking about a beam, the transverse reinforcement is the stirrups. So let's go back to our exam on Wednesday. If I have number 3 U-shaped stirrups, what's the area in shear? 0.22, right? And what's the stirrup spacing? 8 inches. So this is 0.22 square inches, and this is 8 inches. So what's your KTR value come out to be? Say it again. 0.367. Do I have a second on that? So let's continue this out. What is C sub B plus KTR over D sub B going to be? It's not going to be 1.5 anymore, is it? Because here it was 1.5 because that was 0 inches. What does that come out to be? 1.867. Everybody following this? And so now what I want you to do is I want you to compute an updated development length. So what happens to your development length if you replace this 1.5 with 1.867? What do you get? What's that? Smaller number. No, really, what is it? I'm curious to see what the value comes out to be. 40, but essentially 44 inches. Now, do I have a second on that? Okay. So look at what happened here. So This was the worst case scenario, with not considering the transverse reinforcement at all. And if all you do is just compute that KTR value, your development length drops like 20%, okay? And so what I'm going to go through over the next few lectures are a number of ways to take that development length and reduce it. Because ultimately, we have to figure out a way of ensuring that the adjacent element has enough room to develop that reinforcement appropriately. So that's going to be something to discuss over the next few lectures. But in short, there's a couple of different ways to go about that. Next time, what we're going to do is we're going to continue on with this. We're going to take example 16b, which changes up some of these parameters a bit, and the overall answer will change a bit. And then after that, we're going to go back to my final example with the tug of war, and basically what happens if you change the geometry of the bar. Instead of dealing with a straight bar, we deal with a hook. And so that drastically changes development length. That's all I have, though, for you, everybody. You all have, well, those of you who aren't in steel design, have a wonderful weekend. Everybody else, I'll see you in a few minutes.